you can see from here that it's a global problem. So it's a global problem all over the world, where we have respiratory problems of influenza transmission and the way we are living. And these statistics are provided by WHO. And since part of the world, we cannot avoid that. How many of you have heard about that? I'm pretty sure all of you must have heard about Tamiflu, right? And now we need to understand what's the mechanism of action for that and how and why we need to give. And Roche is making a lot of money on that. But oseltamivir, that's probably the name of it. And then again, I'm just going to show you some of the posters there, which I picked up from clinics. I'm pretty sure that if you're waiting for that public information, and it's always good to know. I'm not going to spend much time on that. I'd rather spend time on the virology part of it. But you can see from here in this particular slide, when people want to find out how it works, Tamiflu, how it works. So you can see this is a layman information given to the public in one of the posters. So flu virus enters cell, creates many copies of itself. Public information for a layman, for this even school kid. And we also talked about neuraminidase, which is an enzyme on the surface of virus, helps it to break free from the virus. So that's an enzyme over there, helps to release the virus from the body out. And you can see Tamiflu is a neuraminidase inhibitor. So these are the three basic messages before we go for the influenza for public information. This is something that people already know. And then again, the producer makes this in terms of how much is used and what's the price and so on and so forth. Okay, so I'm just kind of updating you as to what people know and what we need to know a little bit more than that. So RNA virus, still orthomyxovirus, that's a technical name for that, influenza. Most prevalent and significant viral infection that we have ever seen, right? It comes in epidemics, right? And it has occurred in ancient times as well. They think this is the most famous one, especially the pandemic, which occurred in 1918 to 1919 and killing 20 to 40 million people at one time. So you can imagine it kind of like a plague has eliminated. So more people have died, from influenza than the battles of World War I, for example. So that's a serious issue. And then again, this particular virus has occurred over time. So that's another pattern. People are studying that 1918, 47, 57. So they are thinking, why is it that kind of comes after very specific? So they want to learn at the epidemiology of viruses. And then again, till we have an avian influenza virus in Hong Kong in 1997. And things have improved that now we have studied viruses and we have come up with some of the drugs, right? Other than at that time, probably they didn't know about viruses. 20 to 40 million is a lot of people over here. So if you look at the timeline of deaths, for example, for viruses, so you can see we talk about the plague, right? We talk about cholera, we talk about all these different things over time as the history of mankind. But you can see the most recent player in this case happens to be flu. And then again, one of the objectives for CDC and your and all of us is to call emergency preparedness. So CDC is tasked that, let's say, if 50 million people get sick with this virus, what is the preparedness for that? So that's a challenge in terms of stockpiles of vaccine, in terms of stockpiles of antiviral drugs, in terms of panic, so on and so forth. It's just like whatever you saw in the bioterrorism slide. And again, it will just give you an idea what happened in the past. In 1918, for example, they had to create artificial hospitals, right? And then so many beds were there and so on and so forth, to such an extent that there was a pandemic. And is totally out of control, and it also shows our kind of a problem in terms of looking at the public health measures. Now, the other thing is a recent file that you can see from here, 1918, 1919, second flu, 40 million. But I want you to pay attention to H1N1. So H1 is heme agglutinin, and N is neuraminidase. So these were those spiky things on the cells which are there. And I just told you neuraminidase is an enzyme that viruses carry to break them away from the cell so they can go infect other cells. Then you go over here in, let's go from 1977, Russian flu, H1N1, because they want to trace it up. We don't know how many people died because of lack of availability of statistics. 1968, Hong Kong flu, but now you see H3N2. What does it suggest to you? The virus mutated. So even if you prepared a vaccine for H1N1, no good. Because it comes up with another configuration. Then they found out 1957 Asian flu H2N2, which is different than this one, 1.5 million death. And then again, many things are happening, and this is a global problem that we are dealing. Okay. Now, I just picked up this from one of the WHO resources that we need to maintain a catalog. For example, 1918 till I would say 1957, we were playing with H1N1 because good enough that we were abilities to type this. And again, these are those spikes that we talked about, heme agglutinin and neuraminidase. So these are those kind of spiky glycoproteins outside. And as I said, I'm not going to take you detailed biochemistry to exactly tell you what these structural elements are, but you can see that virus mutates. And then over here also, we see a lot of mutation. Not only that, we have H5N1, we call a bird influenza outbreak in Hong Kong, South China, Korea, Japan, and other countries. Okay. And then as of February 26, 2006, we have H5N1. So you can see the challenge we have in terms of, and that is flu, that is influenza, and that's the challenge for all of us as a part of the health community. Now, you can see, and I would refer you to the WHO statistics that they maintain the reports, but I want you to emphasize over here that you can see US was a target for quite a few viruses, which were very significant in many states to create a panic, right? So these are some of the things then you have to deal with it as a public policy or a health policy. And this is a new human influenza H1N1, and these are laboratory confirmed cases and deaths. So these are, you can see the total number of deaths that had happened. And in 2009, I'm just giving you the 2009, the laboratory confirmed cases as reported to WHO. Again, you will see whole of North and South America is involved. China is involved. Australia is involved. And some of the countries, when you see Central Africa, part of Asia, you see it as white. The problem is that maybe they don't know. This was not laboratory confirmed because they may not have facilities to do that. That doesn't mean that they're virus free. Is the point? But again, at the same time, it's more of a panic response that may happen in the West as compared to any other part of the world, which they would never know what's going on. So that's what the ignorance is. Ignorance is a blessing. Anyway, if you're wise to it, that's a complete statement. Orthomyxoviruses A, B, C, only A and B cause significant human disease. They all have a enveloped, segmented, negative sense RNA. Again, remember when I showed you the first picture, I said keep an eye of the segmented portion, segmented, right? Because this segmented genome allows these viruses to develop new strains, to mutate. They reassort their genes and come after human and animals, especially influenza A. Okay. And then again, the next question we're going to address today is that what is the genetic instability? Why do these viruses are genetically unstable? Because there are two important things. One is called drift. The other is called shift. And when I say drift, I mean basically mostly epidemics. And when I say shift, we say pandemic. So pandemic is, all these definitions of these things. The pandemic is going to involve the whole world and a very high incidence. Okay. Now, this is a typical model of influenza A virus. And if you pay attention again to the close-up views over here, and I can see if I can also get a close-up view for you. So you will see over here, there's an RNA inside. They have a nucleoprotein. It comes with polymerase. We have a matrix protein over here, and with typical lipid bilayer, and then two important aspects, neuroamidase and heme agglutinin. That's where the name comes from in terms of either BH1 or N1. So that's important in terms of us knowing that. Now, if you look at, for example, virus A and B type on the left as compared to virus C type, so you will see that they have those special parts that are going to get attached. So we have, again, not only H and N, but some other saccharide chains that are there, so we can get these viruses to attach to the human cells, right? So this will be the basis of what is going on. Now, the mutation that we normally see, especially for drift, the other term for drift and shift is drift, again, as I said, is an epidemic, which is a minor thing. It may be happening in a small community. I usually try to give this example. You're driving, you're slippy, you're going to get drifting your car here and there, but you're still on the track. But shift is like a U-turn. Shift is a major thing that may happen. That's why we call it major change in antigen. So A, heme agglutinin antigen, neuroamidase antigen, because it being provoking immune response. Okay. Now, if you were to look at them in terms of the number of protein, name of the protein, HA stands for heme agglutinin, and NA stands for neuroamidase. This attachment to cell membrane is required, and this is released from membrane. That's why I said Tamiflu is a neuroamidase inhibitor. So that's the difference between these two, and you need to understand that. And again, if you look at the structure of the gene segments which are there within the cell, you can see from here, they may be coming from different origins. So this is like mixing and matching that we normally see. In this particular segment, if you pay attention, that it may be let's say an avian polymerase. It can be human or swine origin, human or swine. So this can be mixing and matching of these genetic elements. That's why when you have swine flu, how does it influence? There's a bird flu. So this is something that we need to understand. And I'm going to spend some time on that. Again, if you look at the structural element of this molecule, heme agglutinin plays the role when it goes and binds to the polysaccharide chain on the cell surface. And that will be the beginning of injection of viral genome. So heme agglutinin is going to agglutinate, bring it towards it. Whereas so one is like for entry and other is for exit. That is like very general information. Neuroamidase is there when it wants to bud off, to break apart from that. Whereas in influenza C virus, you can see over here, they also have a heme agglutinin, which is a fusion protein. They may have some other nucleoprotein with the cell, but some of the specific things are lacking for influenza C to be of significant concern as far as the human disease is concerned. Now, if you look at the infection over here, then again, this is the structure. and you can see all those molecules expressed over here. And this is the RNA genome. The very first step, it has a receptor over here. Let me see if I can enlarge that. So you can see from here, the very first step, that there's a receptor. And remember, I said I don't want to overburden you for you to know the details, what chain is there, and alpha chain or beta chain or whatever, but you know for sure that this receptor needs to attach to this virus before it penetrates by endocytosis. And then again, after endocytosis, it is going to go and have all those macromolecular synthesis of this. And then once it is mediated, then finally it will pick up the outer membrane from the cell's own structure. For example, if it infects a swine, for example. So it's going to pick up the outer membrane structure of the swine's outer cell membrane, and also get some of the genetic materials from within. The reason being, because when the translation and transcription is taking place, that is of course taking place in the nucleus, and you have negative sense RNA over there. So that pretty much will give you an idea as to what the structure element is. And if you pay attention to this structure, you will see that we do talk of some of the major proteins, but we don't want to go at this step to the details of what these structure elements are. But once we, that's where you need a little bit of more genetics, a little bit of more into pharmacology and how the drugs act. I just picked it up from the Nature. It's not even there in the book. So this is the last slide. I'm just going to spend a minute on that. So what you will see from here is that the final disease, as we talked about in bacteria as well, we talked about immune system as well, the final disease is basically a mixture of viral factors and the host factors, right? Viruses come up with an agenda. They come up with a plan. They come up with equipment or whatever genes they are bringing, and they are going to affect the host. In this case, host may be a human being, host can be a bird, host can be a swine, or any other person, right? And then again, the same virus can come out of that, and the whole, if you go back and trace the history of swine flu, so it came from Mexico or some other country, South America, which initiated from farmers in that industry. So both of them got infection from the same virus, and then virus jumps from one to another, and thus it picks up and shares the information of one particular genes with the other. Okay, so that's where we look at different aspects of that. In terms of, but the important thing for this part of the lecture is that you need to know the antigenic shift, which is a minor antigen change, right? Is more of a mutation as compared to antigenic drift. Sorry, antigenic shift is a major thing. So drift, minor, shift is a major. In major, you have reassortment of genes. Genes got reassorted. One gives a local problem in terms of being endemic, present at all time. The other is a pandemic that may influence a larger public or larger world. Okay, so I'll stop here and continue